so today I will try to give you, say, the global statistical picture of this Boltzmann grad limit. So this will be the first lectures. Let's say most of this this part will rely on this cumulon generating function that I defined last time, and so I will start by recalling some important things. So so this lambda epsilon t of exponential h is by definition it's 1 over mu epsilon, the log of this partition function, which is modified by the exponential h. So this is just the exponential moment, actually, divided by the epsilon. And so it can be written as the sum from k equal 1 to infinity of 1 over factorial k. And then you have d nu, say, lambda 1, d nu lambda k. I should integrate this, and a phi of lambda 1 lambda k. So I recall what all these things are. So the d nu here is just the measure on a forest. Okay, so I think it's something like d nu epsilon of lambda is just mu to the factor length of lambda divided by factorial lambda. And then you have that lambdas to be a cluster path. And then there is just the initial measure and the exponential of the sum over lambda of. Okay, so yeah, I think. This is just check that, and then there is the DZL. Okay, so just from the point of view of graphs, what you have is something like a connected graph where everything is connected by collisions. Okay, so something like this. Okay. So here you see that you have both collisions. So this one is a collision, this one is a collision, this one is a collision, and these two are recollisions. Okay, so this graph is connected, but here it is not minimal. And we have seen last time that the contribution of this one will be negligible. Okay, and you expect that only things like this. Maybe like this. Up. Only these minimal graphs will contribute to the limit. Okay, this is minimal. Okay, so that's for the part d nu. Okay, so this really tells you that you have this particle, this set of particles which are connected by collisions. Okay, so this is a set of particles connected by collisions. And then if you remember what we did last time, of course, once you have, say, look at the partition of the space in set of particles which are connected by collisions, you don't have, these sets are not independent just because you should not have any collision between these different sets. And so you have the exclusion of this, and when you expand the exclusion, you get this function here. And so I just recall what phi epsilon is. So phi epsilon of lambda 1, lambda k is just the sum over all possible connected graph with k vertices of the product on all edges of G of -1 lambda I lambda G. Okay, so this means that you have an overlap. Okay, but once again, the overlap does not correspond to a collision. It's just the fact that they will just touch the two graphs will somehow overlap each other, but this will not change the dynamics. Okay, so it's really a mathematical expansion of the exclusion. Okay, so this guy is an overlap. Okay, so now you have many graphs. Okay, so many forests like this, forest like this, and then you have a third one. Okay, I'm not sure that yellow will be really different. Maybe this one would be better, and maybe something like this. Okay, so here you have an overlap. Here you have an overlap. And the others, they are collisions. So this part corresponds to a nu. This orange part corresponds to another nu. This one corresponds to another nu. So you have lambda 1 here. Lambda 2 is the orange part. Lambda 3 is this one. And then you have the phi tells you that these three sets should be connected. Okay. In order that you have this contribution to a cumulant. So a cumulant is really something which the cumulant of order n is a set of particles of size n, which is connected either by collisions or by overlaps. Okay. Okay, so that's for the expansion, and so there are two really important results. So the first one is the uniform bound. Okay, so essentially because you have, so each collision, essentially the cost of a collision like this is like t divided by mu epsilon. Okay, so that's what you should have in mind. Okay, times a constant, say. Okay, because you have a cylinder and this geometric collision, this geometric condition that you have a collision tells you that essentially the cost of a collision, and actually the same cost for an overlap here, is like t over mu epsilon. Okay, and so you see that this d nu lambda, if you just look at the size of this, okay, so you have a constant time to the size of lambda, which comes from the f naught and from the function here, so that's like c to the l. Okay, then you have the mu to the l divided by factor l. Okay, but then you have a factor 1 over mu to the L minus 1, which comes from all this, say, independent clustering collision. And then you have all the possibilities to arrange these different collisions. And this will give you another factor L to the square. Okay? So in the end, you get something like, say, the d nu is something like, essentially like mu. Okay? So you have mu, and then you have the same computation here for the you have 1 over factorial k. You have all possible trees for the corresponding to the phi epsilon. Okay, all these connected graphs. Okay, because you have this tree inequality, so you get a factorial k once again, which will compensate for the 1 over factorial k. And then when you add everything, you get that's essentially the uniform bound here is, and so once again I forget the mu, and so you get a uniform bound. Okay, so, but really what you should have in mind is that the cost of a collision or an overlap is like t over mu epsilon. Okay, and then you look at all possible minimal graphs. Okay, so you have all this clustering. So this maybe I should say maybe the cost of a clustering collision or overlap is like T over mu epsilon. And then essentially you have this factorial K, which come from all possible arrangements of these different collisions and overlap. And then you get exactly that this guy is uniformly bounded. Okay? So it's even it's better than uniform bound. It's really a uniform convergence of the series. Okay, so this gives you a uniform convergence of the series. So as a function, for instance, of exponential of h. Okay, and the second thing that we saw last time is that in the limit, okay, so in the limit, so the first thing is that you can remove all non-minimal graphs. Okay, so that's the first thing. So non-minimal graphs do not contribute. So that's the first important ingredient. And then the second ingredient is what you can say about this collision or overlap. So now you have only the clustering ones, okay? And the way you can parameterize these collisions and overlaps, and then you end up with a singular measure here, okay? So of collisions and overlaps. So now you see that if you have a collision between two particles, okay, so now in the limit the collision will be just pointwise, okay, and so the only thing that you need to know is the angle. So maybe here I should say that, okay, maybe these are not a straight line, okay, so they are. You have the velocity v1, v2, v'1, and v'2 if you have a collision. Okay, so now you see that you can parameterize this collision, okay, by the time of the collision, okay, one position. And now if you have the velocity and you know the time here, you see that the position of this guy is completely fixed. And so the last thing that you need is just to know the parameter here of the deflection. Okay, so each time, and this will be the same, of course, for the overlap, you don't have so you will not have any deflection, but still you will always parameterize by a time. So each collision, say this parameter omega and the velocity. Okay, so this means that if I already know the position and the velocity of this v1. Then this second particle here is completely determined. So you see that it's especially true as long as the size is not 0. You see that the position here of this v2 will be completely of this so this x2 here. So you see that x2 will be just x1 plus epsilon omega plus minus t v1 minus v2 or something like this. Okay, if you look at time 0, the position here, what you know is that if you look at x2 minus x1, okay, at this time here, it's just epsilon omega. And now you see that it's also x2 0 minus x1 0 plus t v2 minus v1. Okay, so you can retrieve everything just from this parameter t omega and v. Okay. So this means that you can rewrite the limit function here. So this will be the starting point. Okay, so So here what I would like to do is to write the limit for this lambda epsilon t, okay? So it will be a lambda t of exponential of h. Okay, so the first thing that I say is that I have only minimal graphs, Okay, and so you see that either I can first look at all collision graphs and then look at the overlap graph. Okay, but another way to do that is just to say, okay, I will have collisions on overlaps, and I will have minimal graphs, say, with both collisions on overlaps. Okay, so I will have only, so I will have something like this. So I will have a sum from say n equal 1 to plus infinity of 1 over factorial n. And then I will have a sum over all possible, so a graph which is minimal, I will call it a tree, okay? Now this tree is a tree with, say, n vertices. I should prescribe the order here of the collision and the overlaps, okay? And now, of course, I have to prescribe each time if it's a collision or an overlap, okay? So it will be a tree with n vertices, an order, and for each vertex, I have to say whether for each node, I need to prescribe whether it's a collision or an overlap. Okay, so this is a tree. So it's minimal, so it's a tree. With n vertices and of an order, and you have signs on each edge. Okay, then I will have an integral here. So you see that each time that you have a mu, say mu times what will become the singular measure is just that each time you have a mu which compensates for the size for this t over mu epsilon. Okay, so that's this part which becomes a singular measure. Okay, so all this mu, they will disappear to get the singular measure. Okay, so now I have exactly something like this. I will have an integral here, a sum of h of zi of t from I equal 1 to n. And essentially, that's I have to integrate around with, say, dx1. I have to fix one position, okay? And then I have to integrate of Zn. Okay, and I will explain what this singular measure here. So now, what is this singular measure? So of course I will integrate with respect to all velocities. So this is just dv1, dvn. So these are the initial velocities of the particles. Okay. And now each time that I have either a collision or an overlap, I have to integrate with respect to time, to omega, and the v now is fixed. Okay. So I have to d omega n minus 1, dt theta n minus 1. So these are the angle and time of the collisions and overlaps. And each time that you have a collision and overlaps, we saw last time that, say, the indicator function of the cylinder, so mu epsilon times the indicator function of the cylinders will give you direct mass times the V, say, the product on all edges of the tree of, say, Vi times Te minus Vj times Te minus times omega E plus. And then you multiply by Se, which is a sign. Okay, so you have the sign here. So it's minus if you have an overlap and plus. Okay, so this Se is plus 1 if it's a collision and minus 1 if it's an overlap. Okay, so that's really say the part which comes from this indicator function that you have to be in a cylinder to get this collision or this overlap, multiplied by mu epsilon. Okay, so that's really the limit of this. Okay, so this is a bit strange measure, but you see that, okay, you see that here in terms of dimension, maybe you see that this omega each time is in a sphere, okay, and you have a time which is a real parameter, so that's really like a variable in RD, okay, as d minus 1 times r is just like RD. Okay, so and in terms of dimension, it's okay. This guy just come from the indicator function of the cylinders. And now maybe a question is, so now how you define this guy, Zi, once you have all these parameters? Okay, so Zi will be just the position of particle number I at time t. And the way you can reconstruct this dynamics, so you have to reconstruct, so the limiting dynamics can be reconstructed from all these parameters. Okay, so at time 0, what you know is the position of x1. Okay, or the position of any particle. One position, maybe the position of the center of gravity or whatever you want. Okay. So then you know the first collision, so maybe the collision between I and J, okay? So if you know that the first collision is between I and J, somehow what you know is the first little bit of something like this, which is, so maybe I could assume that okay, I will not assume anything at this, okay? So what I know is that I have this small part of the tree between I and J, but you see that at this moment I don't know exactly where, so I still have a degree of freedom of translation of this small part of tree. Okay, and so you see that you will know exactly all the position, and once you have this big graph, so you know the graph, you know T, okay. So you know that here this is maybe an overlap, maybe this is a collision, maybe this is a collision. Okay, so if you know here the position of this one, the velocity of this one and the velocity of this one, and you also know at the time at which there will be the collision, then you see that you can reconstruct this position here. Okay, so but you see this is a different way of parameterizing everything. So you will not fix all the velocity and all the position at time 0. Essentially what you fix is the position, say the time and the parameters of all these collisions and overlaps, and then you can reconstruct, okay, the initial position and also the final position. Okay, and Zi will be just the position of particle number I. Okay, so this is Zi of t. Okay, so you see that if you have a big graph, of course, it's a bit complicated to reconstruct everything, but you see that there is no obstruction to do that. Okay, is it okay for everybody, or this is a bit? Okay, so that's essentially what I wanted to say about this limiting cumulative generating function. So of course you have the sum over all possible trees. Okay, so you see that's a kind of complicated formula, and maybe at some point you can say, okay, but so what can you do with this? Okay, so that's what I would like to do today. So the first thing that I will do is to retrieve the Boltzmann equation from this cumulative generating function, okay? And then I will also prove that from this cumulative generating function you can find an equation which is an Hamilton-Jacobi equation which is satisfied by this guy, okay? And then you can also get central limit theorem and large deviation, and so everything from this representation, okay? So I will start with the Boltzmann equation. So the first thing that I would like to say is that the Boltzmann equation is the equation that governs the expectation of the empirical measure. Okay, and I recall that you find the expectation of the empirical measure just by looking at the first derivative of this guy at h equals 0. Okay, so this is a computation that I did last time. So if I would like to look at the expectation of, say, pi epsilon t tested against a function h here, what I have to do is to differentiate, say, d over du of lambda epsilon. I don't remember whether epsilon is maybe here, at u equals 0. You can just do the computation. Okay, you have the exponential moment, then you have one. Okay, so let's do that and then of course, as everything is analytic and you have uniform convergence of the series and blah blah blah, then what you expect is that the derivative of this guy for fixed epsilon will converge in the limit to the derivative of this guy. Okay, everything is analytic, so you have a uniform convergence. So if you have convergence in this of the function to this, then this will converge to d over du of lambda t UH at u equals 0. So of course, you see that you need that it's on this small time for which you have uniform convergence of the series, so it's only for small times. Okay, so for t small enough. Okay, so now you can look at this, okay, and try to see what you get when you differentiate, okay, and so you get the sum from n equal 1 to n of to infinity, sorry, of 1 over factorial n. Then you get the sum over all possible trees, and then you get this. And then here, you see that you will get the sum from I equal 1 to n of h of the I of t. Then you get the exponential of UH, but you see that you will take the derivative at u equals 0, so it's just 1. And then you get dx1 and this singular thing. Okay, so maybe here written like this, it's not clear that it's completely symmetric because I took this x1, but I could take maybe the center of gravity, everything will be the same, so it's not really important. And so you see that one thing here is that you have exchangeability between all the zi here, and so I can just say that it will be equal to the sum 1 over factorial n minus 1, then the sum here over the trees. And then I just have one of this, which is h of z1 of t. And then I get this. Okay, so this means that essentially what you have to do is to test this function h on the position and velocity of the particle number 1 at time t for all possible dynamics like this. Okay, that's what you have to do, and then you have kind of weighted average of all this position and velocities. Okay, so you have a complicated measure here, but then the only thing that you have to understand is what is the configuration of particle number 1 at time t. Okay, that's the only thing that you need to do. Okay, so on all possible graph like this. Okay, so maybe at this point it looks like a bit complicated, but we will see that actually this is essentially enough to get the mild form of the Boltzmann equation. Okay, so actually there is a first term that is somehow special, which is the case where you have only one particle. Okay, of course, if you have just one particle, you just have free transport, and then you don't care. Okay, so this term with n equal 1, okay, is a special term that I will deal with separately. Okay, so I will have first this term, which is just h of z1 of t, and then you have f0, and then okay, so this guy actually you will not integrate. It will be just so it will give you just f0 of x1 minus v1t and v1. Okay, so that's just a free transport. So this is the case when n is equal to 1. Okay, so this will give you exactly the integral should be the integral of f of t x v times h of z dz. Okay, that's just what you get here. Okay, and then you have all the other terms, and these other terms, what you would like to say is that maybe you can write that it's the integral from 0 to t. Okay, so what you expect is that the second term, so what you would like to prove is that this guy is equal to this plus the integral from 0 to t of, say, the transport s, t minus s, applied to this q of ff at s ds. Okay, so that's just a mild form of the Boltzmann equation. Okay, I recall that the Boltzmann equation is dtf plus v grad x f equal q of ff. So if you now integrate, so you call S the group which is associated to this transport here, you get that f is equal to st of f naught plus the integral from 0 to t of st minus s q of ff of s ds. So that's just the Duhamel formula associated to this. Okay. And S is just a group associated to the free transport. Okay, so I would like to prove that the other term, so this guy, corresponds to all the terms for n bigger than 2. Okay? So what I say is that from this formula here, okay, what I hope is that I can retrieve the Boltzmann equation just by saying that this is nothing else than the Duhamel formula. Okay? Just ask question if it's not clear. Okay. Okay, so that's the. So now I have plenty of terms like this with n, which is bigger than 2. So I have at least one collision or one overlap. Okay, and I would like to understand what to do with this. So the first thing we have to do is to somehow restrict this graph. Okay, so this is the first step. So the first step is to recognize that it should be something like a Duhamel formula. Then the next step is to somehow simplify, so look at this, the cancellations between these graphs. Imagine that you have a graph like this. I will try to have a non-trivial one because that will not be very interesting. Okay, something like this, and this I will look at particle number 1. See? So particle number 1, say it will be this one. So now I would like to know the position of, or to say when I say the position, it's the z1 of this at t. Okay. So you see that, of course, you need, in order to know the configuration of the particle number 1 at t, you need to know this part of the history, but also then this part of the history, and of course this part and this part. Okay. And what I say is that it's enough actually, because you see that. Okay, of course, you don't need this one because it will not affect the dynamics of one. But for instance, you don't need this one as well, because you see that for this one, it will appear both with the plus sign if it's a collision and with the minus sign if it's an overlap. And both of them, they will just cancel each out. Okay, so what I say is that all these parts, of course, this is just the dynamics after the collision, so I don't care. Okay, but also what but also I don't care about this. I don't care about this one just because, but because here you have a cancellation between the case where you have a plus and the case where you have a minus. Okay, and if you look at, you can just reorder the terms here and see that you get just 0 as a contribution. Okay, so now you see that now you can replace all these completed graphs by just trees like this, where you have only say the collisions and the overlaps, say for the parents of the particle number 1. Okay. So that's the first important ingredient. And then the other ingredient is, and actually it comes, so that's just the fact that you have overlaps and collisions cancelling each other. And of course, here you see that it's really, really important that you have minimal graphs, because of course, if this guy at some point could recollide with this one, it would be a completely different story. Okay, so what is really important here is that you can essentially neglect all these recollisions and say non-clustering overlaps, because actually all these parts of the dynamics will not affect one. Okay?
Up to excuse me, but up to that time, right? Or is it a statement that's going to be true for all times? It's only up to that particular time which is drawn on the board, right?
Yes. What I say is that if I look at this particle number 1, the only thing that I need to know is the collisions and overlaps which are in this tree here.
Okay. All right.
The other one I don't care. Okay? And now you see that once you have this, you get actually this factorization property. Okay, so that's the what I can say is that now if I look at the singular measure, so the singular measures, removing this is the same as removing the part of the singular measure which correspond to this. Okay, so now I have a singular measure which is just a singular measure, just the product on this edge here. Okay. So I can just replace the complicated singular measure by a singular measure which is just a product on these edges here. Okay, but now you see that this singular measure, I can say that okay, let's just go back a little bit until that the first collision or overlap here. Okay, and then what I see is that I have this singular the singular measure corresponding to this. And then what I will multiply is this part of the tree and this part of the tree, but they cannot talk to each other just because of this minimality assumption. Okay, so what I will do is I start from this yellow thing. And say, okay, now I will just look at this as the product of this, the product of that, and then something which is singular here. Okay, so I will decompose the singular measure as the product of the last collision or the last overlap times two things. So that this is just like a big Fubini, okay? I just look at all this contribution of the singular measure and say, okay, I look at the last time where I have a collision or an overlap. Then I just write this part. So this part will be just, so if this is 1 and say I will call this one 2, this is just V1 minus V2 dot omega plus, so this is the singular measure here, and this is the V1 minus, okay, so before the collision here, times d omega d tau, so this guy is say tau here, I can call it S. Okay. And then maybe, so I will have the contribution of this one, but also of all possible, all yellow thing here, all possible trees, but this is nothing else than the solution of the Boltzmann equation, say, at this time S. Okay? So you have this part with the sign plus for the collision, and the same, the other one with the sign minus, so you have the collision here. So this is the contribution of the collision, and you get f of x1 v1, so f of x, so x is the, x here is the position here minus v times t minus s, and then you have this something like this, okay, minus v t minus s, and you have the v2, so the v1 and the v2, and this is v prime 1. Okay, I call it this v prime 1, this v1, this v2. Again, what I say is that if I sum over all possible trees and the singular measure, which correspond to the part which is above here in this branch here, and the same for this branch here, I get exactly the solution of the Boltzmann equation at this time S. Okay? And same, so if you look at the overlap, there's something similar with a minus sign. Omega ds, and this time you have no scattering. Okay, but you see that it's really important that what you see is that you get the f of v before the collision each time. Okay, so you get exactly the okay, so here you have f of x minus v1 t minus s v1 and f of x minus v1 t minus s at v2. Okay, and the s is missing. Okay, this is s f of s x. Okay, so what I say is that really at this point you use, say, for both steps, you really use the fact that the graphs are minimal. Okay, here you need that the graph is minimal because, of course, this collision or overlap will not affect. So you see that there is an exact compensation between because, of course, if you look at the collision and at the overlap, the velocities after the collision will be different, but you don't care. You don't care where the particles here and here will be. It will not change the weight, and it will not change the dynamics. So it's really important that at this point you don't have any recollision, else it could change the thing, okay? And here, of course, it's also very important because you need that when you cut one edge in the graph, you get two different connected components. Okay, they are not connected anymore. Okay.
May I ask a stupid question? It seems to me that what you said here, you
yes.
just step back from time s,
yes.
and there you have already a time s factorization. So if I remember, in the original proof by Lanford, he would always bring back the thing all the way back to t equals 0.
Yeah.
So is that a difference with this presentation? Is this different from the original proof?
So the presentation is different, but the argument is not different because you need really to look at the complete slice of time to remove the non-minimal correlation.
Okay.
So you first remove all these non-minimal things, and once you have this, you can you can get the equation, say it's almost like, okay, a differential equation, really. But this is because before you did the work to remove all these correlations. So somehow it's not different in the sense that you cannot say, okay, just forget for everything. I will try to do the same thing here without, say, just as a local argument. It's not local because I need to be really on this time interval to remove the non-minimal correction.
Yeah, so your argument here seems that somehow you already here get a semi-group property,
yes,
and it's not for free. I mean,
no, I already did it. So I already get this limiting cumulative generating function. So that's I already did the work.
Okay.
But yeah, then this is really a semi-group property here. Yeah. So of course you need you see that here I'm checking a little bit because I need to prove that I can define this guy here. So I need a bit of regularity. So I need to go back to this series expansion here to prove that actually I have enough continuity with respect to x. Okay. So what you can prove from this representation here, you see, and actually it's really something that can be seen from this formula here, that you have this kind of translation, almost translation invariance with respect to x. So the singular measure here, it's essentially you can prove that this part here, everything will be L infinity, so continuous in x so with measure with values in the space of measure. Okay, and this continuity with respect to just x is enough to define this. Okay, so essentially to justify this, you need the third step, which is to prove that you have enough regularity in x to define the product. Okay, and so essentially what you can prove from the series expansion, you actually get the continuity. And with values in the space of measure. Okay, and this is really related to this translation invariance. And you see that if you would like to do the same in some domain with boundaries, so of course there are a lot of technical difficulties, but one difficulty is really the fact that all this thing that where you use the fact that you can reconstruct everything here. Once you have this omega and this t, you can reconstruct the position here. Of course, you can do if you have a boundary, but maybe you will eat the boundary, and so everything is much more complicated, and it's not clear what you can prove exactly. Okay. Of course, there are many other problems, but this is one of the problems. Okay, so that's the way you can retrieve the Boltzmann equation. Of course, you can say, okay, this is just a difference proof, but it's not really better than that what was done by Lanford. So now what I would like to show you is that with this limiting current generating function, you can actually prove much more. Okay. Okay, I think this at the moment. Okay. So the next thing that I would like to do is to derive the Hamilton-Jacobi equation for this cumulative generating function. Just check that I didn't forget too many things. Yeah. Okay, so here what I can do is to start, say, as exactly I did for the Boltzmann equation, so with this kind of heuristic argument. Okay, so what you would like to do is to look at the evolution of this exponential moment. Okay, so I can do exactly as for the Boltzmann equation. So I can just try to differentiate with respect to t, or maybe I can just look at the small increment with respect to time and just look at the difference. But you see that essentially you get the same. So when you differentiate this, you see that either you have no collision here, and you will get some transport term. Okay, so you get which comes, so for I with no collision. Okay, so essentially you get exponential of sum of the expectation of this, and then you get the sum of vi grad xi of h term like this. Okay, and then you get collision term. And here, so it's a bit more complicated. So now I will just take apart the two particles which collide. So I will have a sum over I different from j, and both I and j. So probably here. Okay. At the moment I look at this, of course, you see that there is a 1 over mu which will compensate this mu here. Okay, so now I have this I different from j, and I will essentially have something like h of z1 plus h of z2 plus minus h of exponential minus h of z2 minus, and then I have the sum from I have the exponential of the sum for I different from 1 and 2 of the h of the I of t. And of course I forgot the direct mass. Of course I should have a collision. Okay, so I have something like delta of x1 minus x2 equal epsilon omega. And I think that's it. Let me just check. No, there is the v1 minus blah blah. And there is a factor 1/2 here because I have the v1 minus v2 dot omega plus. Okay. So essentially you see that it will be essentially the same as for the Boltzmann equation. So you see that now if I would like to keep the exponential of all the sum here at time t minus, what you get is that you have exponential of okay, I write this. So I'm pretty sure that I will erase everything that I should not erase, but okay. Okay, so for this second term, so and of course you have, so you can prove that the other terms with more than one collision, they are negligible. So this is exactly the same argument, just because of the size of the different cylinders. Okay, so you get something like this. So you see that in the first sum, you have something which is like 1 over mu epsilon, but it will essentially disappear with the, because you have 1 over mu epsilon, the log of this guy. Okay, so the mu epsilon will compensate for the mu epsilon here. Now here you have a double sum, so it should be something of the order of mu epsilon square, the second term. But you see that because of this, when you parameterize everything in terms of omega instead of x2, you will cancel one of these mu epsilon. Actually, it's exactly the same thing as for the Boltzmann equation. So you get something which is very similar, and I will try to write it. Okay, so you can just rewrite it, say the second term, as this expectation here, different from J, and I will write h of z1 plus h of z2 plus minus h of z1 minus f z2 minus, okay, minus 1. And then you have the exponential of the sum now of everything, of all the zi. And this is at time z minus. Maybe it's important for the factorization. So now you can reparameterize everything with a singular measure. Okay, so this will disappear. Okay. Okay, so now you see that at this point, what you need, so the first one, you see that, say, it will be exactly the, it will give you the expectation of the empirical measure, okay, applied to the function v grad xh under this tilted measure with the exponential correction here. Okay, so that's the first one. And now the second one would be something also of the same kind, except that now you have this, now you see that it's not the expectation of the empirical measure under this tilted measure, but the expectation of the kind of empirical measure of two particles. Okay, so the first one you can just write, you just say that it's a bit okay, so the first one is just the expectation of the empirical measure applied to this v grad xf, v grad xh, and this is the expectation. So this tilted measure is just, so the tilted measure is just the one that you have modified by this. Okay, and the other one is the expectation of the pi 2, okay? So that's the, you have two particles here, and now you are looking at a function which is the integral of exponential of delta h minus 1. Then you have this v1 minus v2 dot omega plus, and then you have a d omega, the delta x1 minus x2 epsilon omega, the d omega, and the dv2. Yeah. Yeah. Okay, but now you see that this empirical measure acts on function of two variables. Okay, and so what I would like to test is this function p2 on this function of two variables, so x1, x2, v1, and v2. Okay, that's what I would like to do. And once again, the additional mu epsilon here just disappear with this reparameterization of x by the omega here. Okay, so now the important thing is that, so this pi 2 epsilon, okay, the expectation of pi 2 epsilon is just the second marginal, okay, up to a diagonal term that's, okay, we will not care about, okay. So expectation of pi 2 epsilon, this corresponds to the second marginal. Okay, and now I recall that by definition, the cumulants, the second cumulant, is the difference between the second marginal and the tensor product. Okay, so now the second cumulant, which is the second derivative of lambda, epsilon t, this is equal to the second marginal minus the tensor product. Okay, so this means that I can rewrite this guy as the sum of two terms, one which is given by the tensor product, and another one which is a correction which comes from the second cumulant. Okay, now the second cumulant, what we know is that it's smaller by 1 order of mu epsilon. Okay, so of course for fixed epsilon I will get this additional term which comes from the second cumulant. Okay, but in the limit, what I hope, and actually what we can prove, is that the second cumulant will disappear. Okay, so actually you have a formula here. So for this guy, which is that it's d over dh of lambda. So that's the tensor product. Okay, the first tensor product here. So I just write the formula for some pi 2 here. Apply to a product, say G1, G2. So this is a general formula here. So it will be this term applied to G1, G2. So that's the tensor product part. Okay. Plus another part, which is 1 over mu epsilon, the second derivative of the lambda, epsilon, applied to G1, G2. And actually, there is another correction which is due to some diagonal term. I will not really care about that. And here we get the product. Okay. So, of course, all this is for fixed epsilon. But now you see that what I would like to do is to say that in the limit, this guy will disappear. Okay, and actually I have proved it, because what I have proved is that in the limit, all the terms which are not factorized, okay, for the same reason as for the Boltzmann equation here, they will disappear. Okay, so here this is kind of not, this is not a proof here, but actually I have all the ingredients to prove this. Okay, and so we end up with the following equation that I will write maybe here. So if I look at this function here, so I don't remember whether. So I will get a first term, which is the term which comes from, so it will be, okay, I don't know how to write it in a proper way. Yeah. So that this is the term coming from the transport. Okay, this guy is just so this guy is just the pi1, and the pi1 I don't remember where is it? Here. Okay. So when I look at the expectation of pi1 under this tilted measure, it's exactly the first derivative of the lambda. And then I get another term, which is something like that I can actually write. Maybe I will just write like this. So it will be exponential of delta h minus 1. The direct mass at x1 minus x2. So now I will just look at the limit as epsilon goes to 0. So I will have this one, the v1 minus v2 dot omega plus. And now I have this di, so d lambda over dh at x1, say, yeah, x1 v1 d lambda over dh x2 v2, and then you integrate, so it's the same x1 to omega v2. Okay, so one thing which is important is that lambda t exponential of, so lambda t is functional on the space of function, and so when you differentiate this with respect to function, you get a function. Okay, and so now this is a function, this is a function, and this just means that you integrate. Okay, maybe I can rewrite this as like this, dx dv, and of course here there is the dx1 d1 which is missing. Okay, so here you see that's a bit formal because of course to make sense of all of this you need to say in which space, in which functional space your h will be, and what it means to differentiate this lambda with respect to h. Okay, so it's not, okay, there is a lot of work to give a proper functional space to make sense of all of this. But you see that you end up with really something which looks like an Hamilton-Jacobi equation. Forget that h now is a function, and just imagine that it's just a finite dimensional variable. Then you would recognize exactly this. So this is the transport part. Maybe you can forget this part at the moment, but then you see that you get something which is like u square, and so the gradient u to the square, and this the dt, which is like the gradient square. Okay, maybe I should stop for 5 minutes right now, and then I will explain what we can do from this Hamilton-Jacobi equation. Okay, so the first comment about this equation. So once again, I did a formal derivation, but you see that what I proved on the limit generating functional, so that you have only this minimal graph, give you exactly the factorization property that you need. Okay, so at this point I just ask you to believe me that you get this in the limit. Okay, and now what I would like to do is to show you what we can deduce from this. So the first thing that you can do is to deduce the Boltzmann equation. You will say, okay, that's the third time that she said that we can obtain the Boltzmann equation, but just let me just do this very small comment. You see that if you differentiate this with respect to h, this will give you the first marginal here, applied to dth, okay? Then if you integrate this guy by part, you get the plus v grad x of this guy, which is just f, tested against h. And then you see that this is exactly the weak formulation of once you have differentiate with respect to h, you see that either, and you take at h equals 0, so if you do not differentiate this part here, anyway, this would be 0. And if you differentiate this, you get exactly the delta h times this guy here. And this is exactly the Boltzmann equation in weak form. Okay, so that's just just one line to get the Boltzmann equation once you have this. Okay, but okay, I know that we already had this, so now I will try to look at the next derivative of this equation, and we will be able to prove. So the first thing that I will try to do is to show you that we can get a central limit theorem. I will try to give you a statement which is correct. So now I look at the theorem that we prove with Thierry and Isabelle and Sergio. So in the Boltzmann grad limit, or low density limit. So mu epsilon goes to infinity with mu epsilon times epsilon to d minus 1 is equal to 0. The fluctuation field that I will so the fluctuation field is just the difference, so it's the difference between the empirical measure, you subtract the expectation of the empirical measure, and you multiply this by square root of mu epsilon, and this gives you the fluctuation field. Okay, so that's exactly as for you know, random variables in general. You take the random variable, you subtract the expectation, and then you just multiply by square root of n. Here n is just this mu epsilon. Converges to the solution of the fluctuating Boltzmann equation. That I will write now, say on some time interval 0t star, which is essentially the same time interval as for the convergence of the series. Okay, and now I have to write this fluctuating Boltzmann equation. So essentially what you expect is that you will be close to the linearization of the Boltzmann equation. So you have a first term here, which is the theta t dt. Okay, so that would be the linearized part. So I just define this operator here. So L of t is minus v grad x, which is just a transport, plus now the q of ft plus q of ft. And ft is the solution of the Boltzmann equation. Okay, so if you look at this, this is just the linearization of the Boltzmann equation. Okay, you keep the transport, and then you linearize the collision operator around this solution, so the mean part. Okay, so that's, and now you see that it's not exactly what you get. Now you have a correction which corresponds to this fluctuation. Okay, so that's the linearized part, and now I have to say something about this noise. So eta is Gaussian noise, which is delta correlated in t and x, and you have a formula for the covariance. So the covariance of this noise, if you test it on the function g, and so we'll just copy to be sure. If you test it on some function h1 and h2, just 1/2 of dz1, dz2, d omega. Then you have v1 minus v2 omega plus this. And then you take f of t z1, f of t z2, and then delta h1, delta h2, z1, z2, z omega. Okay, so delta h is this function here. So the jump of h. Okay, so you see that all this, so both the linearized thing and this covariance, that depend only on the solution of the Boltzmann equation. Okay. So maybe this equation actually is a very an equation which is not very nice mathematical equation. Okay, so it's not clear actually how you can really construct nice solution of this equation. If I just give you the equation like this and say try to construct a solution, it's not completely obvious. Actually, all the classical methods to do that, they do not really seem to work here. So there is one special case is when f is just an equilibrium. Because then you have nice property of first of all you have autonomous equation because nothing depends on time here and nor here. Okay, so maybe a remark that this equation is nice when ft is just a Maxwellian, so an equilibrium solution. And there is many reasons why it's the case. So first of all, say it's autonomous, which of course is easier. Second reason is that here you have a sign on this part here. So for those of you who were in the seminar yesterday, this linearized operator is a diffusion operator, so it has a spectral gap. So you have that L. Okay, with a sign. Okay, it's not on L; it's just on this part here. Okay, on this L. Okay, and the last thing is that this covariance that you get here is exactly compensates exactly the dissipation which is due to this linearized part. Okay, we have a compensation. Between the fluctuation and the dissipation. What physicists call the fluctuation-dissipation theorem. Okay, but in any case, you can do a relatively simple solution of this. While, say, in other cases, it's not clear. So the notion of solution that we use are actually very weak solution. And we will say that we have a solution of this, provided that essentially we have a Gaussian process and that the covariance satisfies the right equation. Okay, so we will call a weak solution of this. So in general, we define a weak solution of this equation by two properties. The first property is that zeta is a Gaussian process. And that the covariance of zeta satisfies the corresponding PD. Okay, so there is at no point where we really say that we have this equation. Okay, so this equation is just a formal equation that should satisfy a Gaussian process with the covariance that we have. Okay, so that's a bit different from saying that we can construct, okay, just take this equation and construct a solution of this. Okay? So I will not give the proof in details, but I will just tell you some ingredients of the strategy, and you will see that it's not very complicated actually. So actually this is a proof, there are 3 steps. So the first step is to prove that the limit process will be a Gaussian process, so the convergence towards a Gaussian process. And for this, we will use the characteristic function. Okay, so that's a very classical way of looking at convergence of a process. Okay, so the characteristic function is just the log of the expectation. Well, actually, it's the expectation of exponential of I, the sum from I equal to 1 to k of d theta L. So I will explain everything. Okay? Okay, so that's what I would like to look at, and I will just add here square root of mu epsilon. And this actually is just mu epsilon times lambda exponential from capital H. Okay, so I will explain everything here. So here this zeta epsilon is the fluctuation field which is defined above. Okay. Now you see that, of course, it's a function of, it depends on time. Okay. And of course, if you like to look at a process which is a dynamical process, you need to sample this at different times. Okay. So here, this theta L, so theta 1, theta L, there are different times. Okay, so say something times. And this HL, H1, HL, they are the test function for each at each time. Okay, so something functions. Yeah, of course, if I would like to understand something which is dynamical, I cannot just take the thing just time by time. I need to look at all time at the same. Okay, so that's for the definition of this. Okay, and you see that in the definition of the fluctuation field, of course, it's not exactly the exponential moment because I have removed the average part, and so at the moment I just add this part. Okay, just to retrieve the exponential moment here, and then you see that this h is the sum from I equal 1 to L of some. What I would like to look at is I will look at HL of the L at time of the I at time theta L. And of course I have some 1 to N. Okay, I will look at something like this. Okay, so it's a bit more complicated than what I did previously, but actually exactly the same proof of everything. So you see that when I draw picture here, I said, okay, I will look at the Z1 here. So I had something like this. Okay, and I said, oh, but I will look at the position of this guy at this time. Okay, of course I can look also at the position of the other guy, but also I can look at the position at any intermediate time. Okay, so that's just a matter of sampling, and everything else is exactly the same. Okay, so that's a bit more complicated because I try to really sample the dynamics and not only the configuration at a given time, but you can do exactly the same. Okay, so that's just a slightly different sampling. And the only thing is that now this guy is just divided by square root of mu epsilon. Okay, because this is here. You see that it's not the empirical measure. It's square root of mu epsilon times the empirical measure, but in the exponential moment, it's mu epsilon times the empirical measure. Okay, so this means that I test on a function which is really, really small, like 1 over square root of mu epsilon. Okay, that's what I would like to do. Okay, I would like to understand this. The characteristic function is just this part, and this part we can deal with it separately. Okay, of course, what is nice is that the expectation of this is this can be removed from the expectation just because it's a constant, okay, and it's a product, so you can just remove it from the logarithm here. So it's just a different part, and so essentially you get the characteristic function here. Okay, and so now it's equal to this guy, okay, and you have to divide by 1 over mu epsilon. So now you remember that you have the expansion with the series here. And so you have a first term. And so the first term, they have to cancel between this part and this part. Okay, so you have a cancellation, which comes from the fact that this term has not been chosen randomly. It's exactly the one which is chosen to cancel the first term in the series. Then you have a term which is, okay, if I write the series, so maybe I should write it here. So it's just the sum of 1 over factorial n. And then I get the cumulant, Fn, applied to exponential h minus 1 to the n. Okay, something like this. Okay, so the first term here will be so the first term has to cancel out just because of the cancellation between this and this. Okay. Then you have the second term, and this one, you see that, so the term for n equal 2 here, you see that this exponential h minus 1 is exactly of the order of 1 over mu epsilon. Okay? Maybe I'm wrong with the mu epsilon is maybe not at the right place, but I think it's okay. Okay, and so you see that this guy essentially is 1 over mu epsilon to the n over 2. Okay, just because of the scaling of the capital H. Okay, so what you see is that all the terms for n bigger than 2, they will just disappear in the limit. Okay, now the term which is like for n equal 1, you expect the cancellation, and then you just get the one which comes from the second cumulant. Okay, so you see that what is important is you have cancellation of the first cumulant. Then you have a second cumulant, which is of the order of 1. And then all other cumulants, they just disappear in the limit. So that's exactly Wick's rule. Okay, so that tells you exactly. So the fact that these disappear, this gives you Wick's rule. Okay, so essentially that you get the okay, so that's essentially the way. So you see that for free, essentially, once you have this uniform convergence of the series expansion, you get for free the fact that you will converge towards a Gaussian process in the limit. Okay, you don't need to write the limit of anything. Just by looking at the different order of magnitude, you get the the fact that you will depend only on the second cumulant. Okay, so that's just, this is really important here. Say only the uniform bound is required for this first step. Okay, so now you see that I would like so there are two other steps. The second one is to prove that you get the right covariance in the limit. So step 2 is to prove that to identify the limit covariance, the limit of the covariance or the limit covariance. Okay, but then you see that essentially the covariance is a combination of the first cumulant and the second cumulant, and so you see that if you start from this limiting Hamilton-Jacobi equation, you can just write an equation for the covariance. Okay, you differentiate once to get the first cumulant, you differentiate twice to have the second cumulant, and then you just look at the good combination of the two, and you get the covariance. And maybe I can just give you the formula for the covariance and just show you what it means from the graphical point of view, because I think it's more interesting than just proving this. So if you look at the covariance, so now it's the covariance of zeta, not the covariance of the noise. Okay, so you get two terms. So one which is, so you transport here the test function h2 from s to t. Then you multiply this by the function s1, h1, and then by f at s, plus a second part of the integral. So that's the part essentially which looks like actually W. And then you have okay, f of tau, and then you transport from tau to t the h2, and from tau to s the h1, and you take this at xv and this at xw, and this guy looks like the collision operator. So R12 of gg is just the integral of g of z'1, g of z'2 minus g of z1, g of z2. And then you still have the same measure as usual, so it's v1 minus v2 dot omega plus delta x1 minus x2 and d omega. Okay, so now this seems a bit like a complicated thing, but what is important is actually this covariance is given. So this first error comes from the fact that you can have one recollision or one overlap. Okay, and that's what I would like to do. I would like to try to draw a picture to show you this. So so not right now. I have no. I should have one. Okay, maybe like this. I think I have a running collision like this. This is a collision, this is a collision, this is a collision, this is a collision. No, this one is not. This one is, and this is a recollision. Okay, so what we have is that essentially the covariance is due to the fact that you have at least one recollision or one overlap here. And the way you will write this is to, so this operator R here gives you exactly one recollision or one overlap. Okay, and then you have your test function, and you will just transport your test function around trees. Okay, if you remove this, you see that you will get this one with all this part here. Which is, and this part with the other part here. And now maybe you should remember that this H1 and H2 you test at two different time. Okay, and that's what you get when you test at time. Okay, maybe my picture would be just. So this is one time here, which is S, and the other time is T, and T should be because you go until S here, and you see that now here you know that for this part here you will test with the H1. I think it's H1 at time S. Okay, and the other one, you will test them at time t with the function h2. Okay, and then you try to connect them by one recollision or one overlap. Okay, so that's essentially what it tells you. So here this depends on. Essentially, that's what you have. You transport here this. So this U star is really a transport. So this is not just free transport. It's transport plus linearized. So this U star is really represented by a tree. Okay, where you branch. It's so the U star here is just something like this. Okay, so all these guys. They are connected to the solution. So this is connected to the solution of the Boltzmann equation. This guy here is connected to your function h1 or h2. Okay, and so this a branch like this represents this U star. Okay, so you transport the h1, you transport the h2, and then you reconnect them at time tau with a recollision or an overlap. Okay, so essentially you can. So it's the extension of what I did for the Boltzmann equation, where you have no recollision at all, and here for the covariance you have exactly one recollision or one overlap. Okay, and that's the way you can write it. Okay, I will not spend maybe too much time because I would like first to say that there is a third step, and I will not have time to. So once you have this and this, in order to prove the convergence of the process, you need to prove some tightness. Okay, so you need to prove that the soup of delta t minus delta s, something like you need to control this for t minus s small. Okay, and so of course this soup is not very nice, and so at this point you need to use the Garcia, il m'en manque un. Ah oui, Rodmisch from inequality. The idea of this inequality here is that it will somehow control the soup here in an integrated version. So you will control this by something like an integral of, say, zeta t minus zeta s to some power divided by t minus s to some power. Okay, so you will exchange something which is an integrated version, and this is nice because this you can control with this current generating function just by looking at the difference between two times. Okay, now instead of taking a function like this to test, I can just take h of z of t minus h of z of s. Okay, and then I will control something like this in an integrated version, and so this will allow to control this. And actually, there are small issues because you cannot really control this for t minus s, very, very small, so you have to do something else. Okay, so it's a bit complicated, but say the idea is really to say that you can control this guy by an integrated version. Okay, plus other control when t minus s is really small. Okay, because here you see that at the level of the microscopic, at the microscopic level, actually you get something which is not continuous. Okay, so you cannot get something which is continuous in the limit. So, say for fixed epsilon, you see that you have really something with jumps. So you don't expect this to be really continuous. Okay, so that's what you do for the central limit theorem, and since I have only 10 minutes, maybe I would like to state the result for the large deviation, and maybe at some point we can come back on all this if you have questions. Okay, so that's the last part. So I will start with a statement which is okay, almost complete because I will. Okay, so still in the Boltzmann, in the low density limit. So just to come back on this global overview, so you see that I have this empirical measure, which is the thing I am interested in this limit. Okay, so just to see the approximate distribution of particles in the phase space. Okay, so the first thing that we can prove is that its expectation converges to the solution of the Boltzmann equation. Of course, it's not true that it's not like in the mean field limits where everything would essentially really converge to this. You have fluctuations, and so the typical scale of the fluctuation is square root of 1 over square root of mu epsilon, and you can look at this fluctuation using the central limit theorem. But you can ask another question, which is what is the probability to see something which is completely different from the Boltzmann equation? Okay, and that's the question you try to answer with this large deviation estimate. Okay, so what you would like to show is something like this, and of course you expect that this will be exponentially small, the probability to see something like this. So if you look at the probability of that this measure say is a compact, right? Okay, the compact, and this is smaller than the infimum on all function phi which are in this compact of a certain functional which depend on phi. Okay, and we can prove also that the limit inf of the log of the probability to be in some open space, open subset, it's bigger than minus the infimum. And this is not very good. I will try to explain. Of this. Okay, so that's the same as saying that, okay, now imagine that you would like to replace this compact here by say, a small ball around a trajectory here. What you say is that the probability is essentially exponential of minus mu epsilon, okay, so really, really small, times a rate function, which is this f. Of course, if you are looking at a small ball around the solution of the Boltzmann equation, you expect this guy to be essentially 0, and then the probability is essentially 1. Okay, so if you look at the probability of being in a small ball around the solution of the Boltzmann equation, you expect that you will get something which is essentially 1. But if you take a small ball around something else, then you expect that essentially it will be really, really small, exponentially small, and you can compute the rate of this by a functional f here, and this functional f is related to this the solution of this Hamilton-Jacobi equation actually. Okay, so essentially it's so this f. So I have to define this r. And I have to define the f here. So essentially f will coincide with some f tilde, which is the sum of two things. So it's the relative entropy of the initial data compared to the initial data of plus the sup of the integral from 0 to t star of p. So p will be here the test function here, and you have dt plus v grad x phi minus h of phi p, and the h is once again the Hamiltonian, which is in the Hamilton-Jacobi equation. Always the same. 2 minus x1, and then you have a phi of z1, phi of z2, and exponential of delta p minus 1.
So here, your large deviation, it's you need a topology, or it's
yes. So I have to explain everything.
Okay, so it's not like a pathwise or no, okay. You need a. Okay. I mean, if you explain.
Yeah, I will try to explain everything, but I'm not sure I will have time because I promise that I will stop on time. But I will try to explain at least this statement. Okay, so the first thing that I would like to say is that this f here, you can prove that it corresponds to this f tilde on a restricted set, which is maybe not R, but something which is like R. Okay, but the way f is defined here is as Legendre transform of this lambda. Okay, so in principle, okay, once again, so the f is essentially okay, a kind of product that I will not maybe okay, it's phi of t, g of t. So the sup of yeah, g of t minus phi tg and minus lambda t exponential of g. Okay, so the sup here on g. Okay, so that's kind of Legendre transform. So maybe I should just explain why I have these two terms. So what I say is that now a function which is defined on 0t it's the same as giving the function at g at t. Okay. So the way I define a function on 0t is by giving this limit condition here, and by giving this d, and this d here is dt plus v grad x. So what I say is that if I know this function here, and I know g of t, then I know g. Okay, so this part is just a kind of scalar product, okay, between phi and g. Okay, so you have to integrate the transport. That's why it's a bit complicated. But essentially, if you know this transport term and the value of g at the final time, you know g, and this is kind of a scalar product between phi and g, and then you remove this lambda. So it's really the Legendre transform of lambda. Okay, so that's the way, and just using this definition of f, you can prove essentially the upper bound. Okay, so that's okay, and you see that the upper bound, you have no restriction, and so if you take the phi to be really this guy, and you see that, so I still need to define the topology here, and this is a topology which is just defined with it's a weak topology, where I just use the projection of the measure on some function h. Okay, so I take a family of function h, and then I just look at balls around this. Okay, so this is a weak topology, and you see that I have no restriction here, as long I use this definition by the Legendre transform. Okay, and then it's not really this part on the upper bound is not very complicated. Okay, now if you would like to look at the lower bound, it's much more complicated, because you need essentially to prove that, first of all, that essentially you can reach here the soup. Okay, and so you need some regularity of f and so on, and that's why you need here to add this restriction here. And essentially the restriction here is that you will somehow construct everything. So you will assume that the phi which is here is already the solution of some biased Boltzmann equation. Okay, and that you can construct just by hand the g which is here. Just solving a couple of, so you have two Hamiltonian equations which are associated to this optimization problem, and so one will be just the fact that you assume that phi is in this class. Okay, so this R, you assume that phi is a solution of some biased Boltzmann equation. And that it's very smooth, okay? And when I say smooth, it's smooth plus a lot of decay at infinity. Okay, so once I know that the phi is like this, I can construct the g for which this soup is reached. Okay, so g, the g bar can be obtained by solving another equation like the Boltzmann. Can be obtained by solving some backward Boltzmann equation. Okay, so really you should have this picture in mind, that you have an Hamiltonian, so you have an Hamilton-Jacobi equation. So with an Hamiltonian, if you look at the Hamiltonian equation, which are associated to this equation, so just dh over d, so d phi over dt equal dh over dp, and so really the Hamiltonian equation associated to this Hamiltonian here, with some small correction because of the transport, but say essentially that these are the two Hamiltonian equations associated to this Hamiltonian. So you get one forward Boltzmann equation and one backward equation. So this really the Hamiltonian system related to this is a system of two coupled Boltzmann equations, one which is forward and the other one which is backward. So if you can solve this system, essentially you know how to construct here the G, and then you can look, and then the way you can prove this here, and you see that that's why I get this restriction here. Once I have this G, essentially what I have to do is to look at this, instead of looking at this the law of large number for this measure, I have to look at the law of large number for a tilted measure. Okay, so that's what is called the Gartner-Ellis method. So that's for the Laure bond. And so essentially what you are doing is to look at the law of large number. Law of large number for a tilted measure. And this tilted measure is constructed from this G here. Okay, so essentially it's the exponential. So it's the expectation, so that would be the usual measure. And now I will just change it by looking at exponential of mu epsilon lambda, and then I get here, okay, these two terms here. So a kind of product of, okay, I don't write it completely correctly, but nothing is correct here. So pi epsilon g. Okay, so I change here the measure by adding this part with the g bar. Okay, so this is just to get the normalization. Okay, and now if I look at this new measure, I will get exactly this convergence here. Okay, so that's now just the law of large number for this tilted measure. But you see that to do that, I need to know this g bar, and I can really solve all this Boltzmann equation backward, forward, provided I have a lot of assumption. So everything essentially needs to be analytic. So analytic, so the lambda need to be analytic, and I need a lot of decay, so it's really a functional setting, which is really very, I think actually it's a functional space which is very small. So it's not very satisfactory because there are still a lot of room for improvement and to try to remove all this assumption. But at least it's consistent. So you really manage to prove that at least when you are close to some nice phi, you get that the probability is exponentially small, and you know exactly the rate. Okay, so I think I should stop here because I promised to be almost on time, and of course I can try to answer to questions. Thank you very much.
Thank you.
François, say it again. So I'm not trying to understand this business of open and compact sets, right?
So yeah, usually I think so. I think under the control of Thierry, but I think we would be happy with something like this without this restriction here. I think.
Yeah, well, I mean, if I remember, I mean, large deviation, you really need to have open and
yes.
Compact sets, right?
Yes.
Okay. All right. So
the bad thing is this restriction here.
Yeah, exactly.
Yeah.
All right. So, and also the compact set up there. How is it? How big is this compact? Or
I think there is no restriction on the size of the compact. The only restriction is on topology. So we are looking at a weak topology.
Compact sets, you know, I mean, it's a compact set is fairly restrictive. You know, I mean, it's.
You mean you would prefer with just something which is closed?
Yeah, I mean,
yeah.
It's not. Depending on the topology, compact sets might be fairly restrictive. So that's why.
Yeah, it's very restrictive because it's a weak topology.
Yeah. Mm-hmm. Okay, so that's my first. And the second thing is this, I mean, this R, which you said, so that phi is the solution of the time.
The point is that actually we are.
So maybe there's the typo, so it's phi tilde for the open bound and f tilde for the lower bound and f for the.
I think we only prove that f is equal to. I think it's f everywhere, but we can prove that f is equal to f tilde only on R. Yeah, but this is F is this is okay with F everywhere, but here we know that F is equal to F tilde.
On that particular restriction.
Yeah, because we have this restriction here, we know that F is equal to F tilde. And actually, we really need a kind of, actually we have, say in this case, since we know the G bar, you can remove the soup, and then you have something which is completely explicit for the F. And that's how it works. Essentially, we have an explicit representation of F. Yes. That's that we really use here. And to get this representation, we really use that we can get this large deviation functional just by solving the Hamiltonian system, which is associated to this Hamiltonian here. Okay. So essentially, if you can, yeah, that's really the important point. And here you see. Maybe that there is some room for improvements because the Hamiltonian system is the coupled system of two Boltzmann equations, one forward and one which is backward. And actually, Chen Jiawei has worked on this, so on this limiting system, and she has proved that we can somehow solve this Hamilton-Jacobi equation in say much bigger space, which is defined, you know, just with Sobolev norms and so on, and not with, because here we have really, say in the original paper here we have really sets where because of this loss continuity estimates we lose on everything. So there are really analytic sets with very bad norms. So you can really improve, at least to solve this coupled system of Euler-Lagrange equations and solve the Hamilton-Jacobi equation. But then it's not clear that in this setting you can prove the convergence.
Okay.
So this, yeah.
D'autres questions?
Maybe, so maybe I wasn't paying attention enough when you talked about the.
Yeah, but it was not clear at all. Yeah.
But so then, in general, you can't really define this field, or can you?
You know the field because this is the limit of something that exists, so it exists. The zeta. Mm-hmm. Yeah, it exists just because this is a limit of something. Mm-hmm. Okay, so it exists. Mm-hmm. You know that it's Gaussian, and you know that the covariance satisfies the right equation. So if you decide that this is a solution of this is a notion of a good notion of weak solution for the system, then you are happy. Okay. Because you have a Gaussian process. Yes. It exists just because this is a limit of something, and it satisfies the right equation. Okay. Okay. But of course, now if I cannot prove any uniqueness for this, and if I give you the equation and just say construct a solution, then I don't know how to do that.
Yeah, if you don't know it comes from the previous constructions, then you're essentially lost, right?
Yeah, except in the equilibrium case where you can, there are many other ways to proceed.
And because, okay, so maybe I miss a point, but so because okay, you go through this with the empirical measure, yes. And if I do a parallel with some situations where you have strong interactions between particles, sometimes you don't really want to look at the particles, but more at the Liouville equation. With yes. Some noise, you can define like entropic solutions or something. And so would.
So what you have in mind is for mean field?
Yes.
So for mean field, I think the situation is really different because you can have some noise at the beginning, and then the noise will be transported by the dynamics. But you would not have. So if you write the same, you would not have this dynamical noise. Say somehow the dynamics will not produce some additional noise.
Yes.
It's really a very strong convergence not just the convergence of the average, but actually everybody will converge to this mean field trajectory. So it's.
Can you write like some sort of central limit theorem, not with respect to the empirical measure, but with respect to like the cumulants or like density-wise something? Maybe.
I think you see that in the mean field limit, essentially you preserve factorization. So all the cumulants, so probably they are not 0 because at initial time they are not 0. But what you expect is that they should at least keep the same order of magnitude as at the initial time. And here it's not the case, because say at the original time, the fluctuation would be of the order of square root of epsilon to the d, while for further time they're at the scale square root of epsilon to d minus 1. So this is really and another way to say that is that in the limit equation you have some dissipation. And this dissipation, exactly as say, if you are at equilibrium, you see that this dissipation, which is just the kind of the information that you lose, is exactly compensated by this fluctuation. So they are exactly of the same size. And okay, when you are out of equilibrium, it's not clear at all what say we were not able to say that we have kind of enough information encoded in the fluctuations. Probably you need more. It's not clear.
Okay. Yeah, but perhaps maybe in the case of mean field limits, if you're thinking of the setting like in the paper by Brown and Hebb, I think. Of course, I don't think the cumulants have been studied or anything like this. Hamilton-Jacobi has been written in that case, but yes, I mean it's a much simpler situation, right? I mean it's been known for.
I think it depends on the time scale you are looking at. If you are looking at time scale of the order of n, then you get the Lennard-Balescu correction, which would be the equivalent of the Boltzmann thing. And then probably you have some large deviation which are associated to this Lennard-Balescu correction. So I think in the mean field case, in order to see this kind of fluctuations and also large deviations, you need to wait for a much longer time. Yes. And I think this time is typically of the order of n.
Yes, of course.
But then it's not funny, because Boltzmann is already complicated, but Lennard-Balescu is really another story.
But yeah, but I mean, I wasn't asking about doing this for the mean field, but rather like, can you? Well, anyway, okay.
Okay, so if there is no more question, let's thank the speaker for this lecture and for the series of lectures, of course. Thank you.